Conjugate acid of ammonia is NH4 plus. Yes, that's correct. Why? Ammonia plus H plus will give us ammonium ion. Normally, conjugate acid-base pairs are important only for the weak acid and weak bases only. Right? Then it's ammonia. To be conjugate, the difference must be only one hydrogen. Here we have less hydrogen. We have one hydrogen more than the base, the weak base. So this is our base. So this is conjugate base. Sorry, conjugate acid. The one which has lesser number of hydrogen is the base and the other one is the acid. To be conjugate, always the difference of hydrogen must be only one. Here we have one hydrogen greater in ammonia plus ion. So in this case, even if you get that H2S will dissociate giving H plus and HS minus, and this HS minus will dissociate giving H plus and S2 minus. Even in this case, we can get this is conjugate acid either. H2SO, HS may be our acid, then these two will be the conjugate base. Why? This HS minus has one hydrogen less than H2S. S2 minus has only one hydrogen less than HS minus. So conjugate, and this is acid. Acid and conjugate base. If you get this as base, then you can say this is the conjugate acid of this. For both sides, it is true. The only thing is there must be only one hydrogen difference between the acid-base pair. If you get this one, H2S, straight away 2H plus and S2 minus. This is not a conjugate pair. Why? Here the hydrogen difference is 2. So this is the acid, this may be base, but that has no such relationship called that conjugate. Right? But in our case, the ammonia and ammonium ion can be considered as conjugate acid-base pair because it has only one hydrogen difference. So A correct. Second one, NH2 minus is the conjugate base of ammonia. Again, it is true because NH minus plus H plus will give us NH3. So you can say this is the base, NH2 minus, this is the base, and this is the conjugate acid. Or if this is the base, this is the acid, this is the conjugate base, because again it has only one hydrogen difference between these two. So be correct. See, ammonia is formed by reacting between this one and this. Ammonia is formed by reacting between ammonium ion and nitrate ion. Ammonium nitrate and NaNH2. Let's see. NH4NO3. Ammonium nitrate. Will give us actually sodium nitrate and ammonia. Oh, here you have ammonium ion, NH4 plus. This is our acid. And this is our base. These are not conjugate pairs, but acid base. This has an extra hydrogen, this has less hydrogen. So one of hydrogen from this ammonium ion will be given to this NH2 minus ion. Then you will get 2 ammonia. Therefore, it is 2. That is what will happen in this. So C also correct. Then the D. Ammonia cannot act as oxidizing agent as nitrogen. In ammonia exists in the lowest oxidation state of the above. The true statements are, ammonia cannot act as oxidizing agent. Let's see. This ammonia can act as an oxidizing agent, reducing agent, acid and base. Let's see oxidizing agent. Ammonia can act as an oxidizing agent. If you get the sodium react with ammonia, giving soda amide, NaNH2. NaNH2 plus H2. In this case, sodium, zero oxidation state of sodium has oxidized to +1 by this ammonia. So it is, if you balance this, you will get this. So ammonia can oxidize something else. Therefore, it has oxidized. It has as an oxidizing agent. So this can be taken to show that ammonia can act as acid. Why? Normally we know that acid react with metal giving hydrogen. Therefore, this is another example to show that ammonia is an acid and also acid. Then reducing agent. Ammonia can reduce something else. Very common example, we can get this one. Ammonia plus Cu. In this case, ammonia N2 plus copper plus water. In this case, copper is in +2 oxidation state. Here the copper is in 0 oxidation state. Nitrogen in this case -3, but nitrogen here is 0. So you can balance it by putting 3 here, 2 here. No, I'll show you how to put those numbers using oxidation numbers. You can balance it. See, the difference between this one is 2 electrons. The difference between this one is 6 electrons. Why it is 6? Here, you can see that on right hand side you have 2 nitrogen. So you have to consider 2 nitrogen even on the left hand side. Then 1 nitrogen is in -3. So -3 into 2 -6. But all the nitrogen on right hand side is in 0 oxidation state. Therefore, this is here 0. So the difference is 3. Then you have to get the least ratio between these two. 3:1 and interchange and multiply this by 3, this by 1. So this by 3, this 2 is available. So 3 water, now it is balanced. So that is how you can balance it. So in this case, ammonia has act as reducing agent. Even this ammonia can react with Cl2 forming various products, but I will get very common one, that is N2 plus if you have excess of ammonia, say, actually what it forms, N2 plus HCl, but that HCl will react with the excess of ammonia giving NH4Cl. In this case, you can put 8 here and 3 here, 6 here, so it is balanced. You may go through the note, the reactions of ammonia in group number 15. So you will see how really this reaction happens. This can be written as two steps. Why? First, ammonia will react with Cl2 giving N2 and ammonium chloride. Sorry, HCl. HCl is an acid. That acid will react further with the um this ammonia, excess of ammonia, because ammonia is the base. Basic ammonia react with acidic HCl forming this ammonium chloride. So please go through the note and check it. And this is the reducing agent. Then we have seen that ammonia can act as an oxidizing agent and also an acid and reducing agent. Now, the example for base, this ammonia, actually it is available in this one, right? Ammonia can react with acid giving salt like ammonium chloride. In this case, acid then base react together to form this salt. So it is basic. This is an example to show that this ammonia is a base. Therefore, your answer is ammonia cannot act as, that's wrong. Ammonia can act as, so it is wrong. So the answer is 4 part. Only A, B, C are correct. The organic compound X gives an orange colored precipitate with reddish reagent and reduces tolerance rate. Which of the following could be? Organic compound gives an orange colored precipitate with reddish reagent. Then it must be an aldehyde or ketone. Or simply we call that the carbonyl compound. Carbonyl compound. It must be an aldehyde or ketone. Next one, reagent and tolerance reagent. Organic compound exudes an orange color precipitate with ready reagent and reduces the tolerance reagent. Then this is definitely an aldehyde. Why? Brady reagent. Brady reagent is the main reactive part of that Brady reagent is 2,4-DNP. This is called the benzene. And this is called the hydrazine. This is called hydrazine. Right? Then one of the hydrogen can be replaced by this benzene. I will remove hydrogen and attach benzene instead of that, like this. Then this is called phenylhydrazine. Phenylhydrazine. Then in this phenylhydrazine, this is the one with this is our first carbon, then this is second carbon, this third carbon, fourth carbon, fifth carbon, sixth carbon. 2,4-DNP means DNP, dinitro. Here on the second carbon we have a nitro group, and on the fourth carbon we have nitro group. Then we call 2,4-DNP or 2,4-dinitrophenylhydrazine. This is when we add carbonyl compound like aldehyde or ketone. Say you have RNR, R1 and R2. If it is an aldehyde, R1 or R2, one of these substituent may be hydrogen. Then what happens? This will remove as a water molecule. Actually, how it happens? First, it becomes like this. NH NH and this carbon, this double bonded oxygen become OH, but it is unstable, right? Because of instability of that, it will automatically hydrolyze. It means, sorry, the dehydrate. Dehydration means removal of water molecule. A water molecule will be removed automatically, so it turn into this product. Here you have that NO2 group, though I don't write it, it is available, right? And here nitrogen, hydrogen, nitrogen, then double bonded with carbon. This is what we call that dye, or the colored compound. It may be yellow, orange, or sometimes red, depending on the reaction condition and the compounds we use. So this ready reagent will give that orange colored dye or the compound with aldehyde or ketone. So, but it says that tolerance reagent reacts OD reduced by that compound. This must definitely be aldehyde. Then the first one can be because we have this aldehyde group. Second one cannot be because it is not an aldehyde, but it reacts with this given white color compound. That is not because of reducing, it is because of acid-base reaction. Here we have CHO, so it can, but these two cannot. Because here you have ketone and here you have alcohol. So only possible answers A and C. Organic compound exudes an orange colored precipitate with ready reagent and tolerance reduces the tolerance reagent. So it can be either A or C. Therefore, your answer is second one. In addition to this, I'll give you some other things. What happens if you have actually, what happens in this case, say you have this aldehyde. When we add tolerance reagent is ammonical silonitrate. Ammonical silonitrate, why do we use this ammonical silonitrate in this case? See, ammonical silonitrate is the Ag. Say you have NO3. We add in ammonia into this. Then it forms AgNH3 twice NO3 complex. And if there is a thing called that complex ion equilibrium, no need to consider that, but this AgNO3, sorry, that Ag amine complex. This is in equilibrium with Ag plus and NH3. Here, the Kc value is very small. Kc is very, very small. That means the Ag plus concentration is very small. Therefore, the Ag plus concentration is very small. Because of very small Ag plus concentration here, the reaction between this RCO and H is very slow. Right? What happens really in this case? We have Ag plus, Ag will be reduced while this is oxidizing. So we have that Ag plus water here. So this will oxidize, this will reduce. So it will give us C, or say OH and Ag plus H plus C omega kilowatt. Something happens in this way. Then what happens? Here, as the medium is basic, normally we don't get this acid. Acid will react with the base, O minus, and water will be produced because of the medium is acid basic. We are adding ammonical AgNO3. So basic and Ag. So why do we use this ammonical AgNO3? Oh, sorry. This ammonia complex of this because of the very low concentration of Ag, this reaction is taking place very slowly. Therefore, the silver will be deposited on the wall very slowly. Then only it gives us a nice mirror. Otherwise, it will be black. If the reaction is taking place little fast, you will obtain a black color, something deposit on the inner wall of this test tube. As we need a nice silver mirror, we use this. Even though you add AgNO3 only, this will happen, but in this case, you will not see the characteristic silver mirror. That's why we use it, right? Okay, now, and the other thing is, if you have the RC triple bond CNH, when we add ammonical silver nitrate again, here we have that ammonia, Ag plus and ammonium. This is base, so that base will get this hydrogen forming ammonium ion, and Ag will replace by that. So see, Ag, this is not soluble in water, therefore this will obtain as white color precipitate. In this case, it is acid-base reaction, not the oxidation reduction reaction. So in this case, the silver may not change its oxidation state. So it doesn't reduce the tolerance reagent. Right? And the other thing you need to know is this the silver mirror test is only answers for the aliphatic aldehyde, but not for the the aliphatic and aromatic both. Aliphatic means RC or H. Aromatic means something like this, directly attach formaldehyde or this aldehyde group to the benzene ring. But if you get the other reagent, we have another test for this aldehyde. We call that using what is called that the Paling AB. In that case, Paling will react only with the aliphatic but not with the aromatic aldehyde. So you may go through the note and refresh your knowledge. Right? Okay. So in this case, the answer is only the A and C. What is the pH of the solution formed when 100 cubic centimeters of 1 moles per dmq sulfuric solution were mixed with 100 cubic centimeter of 0.4 KOH solution at 25 degree Celsius. The Kw is given as 1 into 10 to the power minus 14. First of all, we have to find the concentration of the excess component. Here we have an acid and this is a base. So acid base will react. We have H2SO4 and KOH. It will give us K2SO4 and water. This is the balance equation. Then you can find the initial amount. Initial amount of sulfuric. It is 0.1 moles per dm cube 100. 0.1 moles per dm cube into 100 into 10 to the power minus 3. Actually, it is 0.1 decimeter cube. So you will get answer as 10 into 10 to the power minus 3 moles of sulfuric. Then the KOH. 100 of 0.4. 0.4 moles per dm cube into 100 cubic centimeters. Then the answer will be 40 into 10 to the power minus 3. And in this case, we know that 1 mole of sulfuric requires 2 moles of KOH. But we have 10 is to 40 or 1 is to 4 ratio. So the remaining amount remain after the reaction, we don't have sulfuric and we have a 20 of KOH and K2SO4 and water. In this case, K2SO4, I don't go in. Okay, quite new. Here we have then 10 into 10 to the power minus 3 moles of sulfuric. Then what happens? In the case of K2SO4, K2SO4 is formed by strong base and strong acid. Normally, the anion of the strong acid, though, cation of the strong base will not hydrolyze. That means it will not cause for the pH. Actually, if you just have that K2SO4 solution, according to the theory, we can say that the pH is 7. Because in such a case, you will get only the H plus and OH minus only from the dissociation of water, but not from the anion or cation available in that. Or this from this salt. But now we have only the KOH. Now you can find the concentration of KOH. Concentration. It is 20 into 10 to the power minus 3 divided by 200 into 10 to the power minus 3. Why? The volume is 200. We added 100 cubic centimeters of sulfuric and 100 cubic centimeters of KOH. So it is 0.1. Now you have 0.1 moles per dm cube solution of KOH. So POH equals minus log OH minus concentration. Now the OH minus concentration is 0.1 minus log 10 to the power minus 1. 0.1 means 10 to the power minus 1. So it is 1. Now we know that pH plus POH equals 14. If the Kw is 14. Therefore pH is equal 14 minus 1 equals 13. So your answer must be the fifth one, 13. Solid A introduced into a closed system comes to following equilibrium when heated to a certain temperature. This is solid. Whenever, wherever you find reversible error, first job is checking the physical state of the each and every component. If you have solid, you have to mark it as solid and you have to remember that. Otherwise, when you write down the KPKC equation, you will include that. Which of the following gives the equilibrium partial pressure of B? Okay, let's see. Now you have 2A solid, B gas plus 2C gas. I assume that because of the dissociation of this A, the partial pressure of B is P, then C is 2P. Why? It is 1:2 ratio. So equilibrium pressure, I take it as P and 2P. Then I can write down the Kp. Kp is equal to Pb into Pc square. Then P into 2P square. What I need is the P. P is the partial pressure of B. So then 4P cube is equal to Kp. Then P equals Kp over 4. And its cubic root. Kp over 4 to the power 1/3. So the answer is 4th one. Remember that if you find any equilibrium reaction or reversible reaction, please check the physical state. In a reaction to the, instead of that, the moles, we can write down the pressure. Why? Pressure proportional to number of moles. PV equals nRT. If the temperature and volume constant, pressure proportional to number of moles. So if you need to find the pressure, straight away you can substitute pressure, or you can take this dissociation and in terms of pressure.